So today we're going to be looking at AC circuits. How many people have already studied AC circuits? Okay, so 4. So that means the majority haven't. Just want to make sure I had myself straight. Resistors, Georg Ohm gave us a nice relationship between voltage and current in a resistor. That is, the voltage is linearly proportional to the current, V equals IR. I have lowercase v and a lowercase I in this equation simply because now we're going to be looking at things that vary in time, and by convention you use a lowercase if it's varying and an uppercase if it's constant. Now I said that's by convention. It's not by strongly followed convention. So you will still see capital V for varying voltage, but this is the best way of writing. Of course, the V parenthesis T, that means voltage as a function of time. I parenthesis T means current as a function of time. So that's just the Ohm's law we've learned. So when we use an AC circuit, a circuit with alternating current, that equation still works for us. Capacitors become a little more interesting. For a capacitor, we define capacitance. Capacitance was defined by the equation. Capacitance is the charge that you store divided by the voltage difference between the plates. When I said the charge you store, that was inaccurate. What word should I have said?
Charge separation.
The charge separation, because you're not storing charge. You don't have a capacitor with, 10 nanocoulombs of charge on it. You have a capacitor with plus 10 nanocoulombs on one side, minus 10 nanocoulombs on the other side, if you're in a normal circuit. So given this relationship, we can write the charge at any time is equal to the voltage at any time multiplied by the capacitance. And when I said the charge, I meant the charge on one plate. When I said the voltage, I meant the voltage difference between the plates. And then given this equation, all I have to do is take the derivative of both sides, and I'll get current on the left side. And so if I do that, I'll have the equation that says current, perfect line, the current through a capacitor is equal to C times the derivative of the voltage across the capacitor. Once again, I used a word that really is not correct. Did anybody catch the word I used that wasn't correct? Not as obvious as when I said the charge stored. I said the current through the capacitor. There shouldn't be any charge passing from one plate to another. So when I have this capacitor, what do I mean when I talk about the current with regards to the capacitor? I always say the current through a resistor to make sure students know we're talking about what's going through. For the capacitor, if I have current that's going like that, what's happening? Okay, I have charge flowing there, and this is the mythical positive charge. And so in reality, that was the same as electrons leaving, and the electrons leaving leaves a positive charge. So that current going to that side of the capacitor means that I'm taking away electrons and it's getting positive. And what's going to be happening on the other side of that capacitor? I'm going to have the current going like this on the other side capacitor, which means that electrons are flowing in and charging that side with a negative charge. So I have a current that flows to the capacitor on one side and from the capacitor on the other side. It just doesn't pass between the plates. Instead, it's charging the plates. So when I said the current through the capacitor was incorrect, it's the current coming to it on one side and leaving it on the other, but it was charging the two sides rather than going through. So it's an important thing for understanding what's going on inside a capacitor, that clarification of the words. Now I put a big box around this equation because it's super important to us in physics. The current coming to or leaving a capacitor is proportional to the derivative of the voltage, to the rate at which the voltage is changing. And so that gives us an Ohm's law-like relationship between current and voltage. What's different? Well, we have a derivative here. And we've already talked about the important implication that you can't have an infinite current, hence you can't have a discontinuous change in voltage. Now we're going to use this in circuits today to see how it applies to an actual circuit. So here we go. This is going to be a circuit that just has a resistor, a capacitor, and a power supply. And so that power supply is, I put here 10 volts, 60 hertz power supply. And I said, let us suppose that this 10 volt, 60 hertz power supply creates a current through this circuit that's I is equal to I max times sine of omega t. So it's going to be a sinusoidal voltage resulting in a sinusoidal current. And then I said, what are the voltages through each element? Well, who can give me, there's an easy answer for one of them. Who can give me the easy answer? The what? Well, through which element? The resistor. Okay, the resistor is the easy one. So the voltage through the resistor is equal to, go ahead, Nate.
It's equal to the voltage divided by resistance.
Current times resistance. You went to the wrong one. You went to the current is equal to. So it's going to be the current times the resistance. So that's going to be resistance times I max times sine of omega t. In this problem, what is omega? Okay, I heard a couple different answers. Who's confident? Can say it loud for me to hear. Okay, it is angular frequency. I want a number for it. All right, it's 2 pi times the frequency. So that's going to be 2 pi times 60 hertz. Or thus 120 pi radians per second. So that's what omega is. I have here my voltage through the resistor. If I know what the value of I max is and the value of R, which I gave you 5 for R, then we would know what the voltage is through that resistance at any time. Okay, so that was the easy one. Which one do you think is the intermediate difficulty one? That's right, the capacitor. Most people would have said, well, the power supply, obviously, and that would be not obvious, and it's not the easiest. It's the hardest of the three. So for the capacitor, we just saw that current, well, I don't need to put C. It's a series circuit, so they all have the same current, is C dV capacitor dt. How can I solve this for the voltage across the capacitor? Before I integrate, I have to separate variables. So I'll separate variables. So I'm going to have my current is I max sine of omega t. I'll multiply the dt across. So I'll have dt there. I'll divide by C because I like to. And so there I solved it for dVc. I've separated variables. And now the right side is only a function of voltage. The left side is only a function of time. I can integrate the two independently and it still has to be correct. So I'm going to switch the sides. Integrating these, I'm going to have Vc is equal to I max was a constant over C was a constant, integral of sine of omega t dt. Notice I don't have limits. It's one of those rare times in life. What's the integral of sine of omega t dt?
Omega.
1 over omega.
Yeah.
So that's going to give me a negative I max over omega c cosine of omega t. Now, this looks kind of like Ohm's law. Let me make it look a little more like Ohm's law, but not exactly the same as Ohm's law. Minus cosine of omega t is equal to sine of, right, they're only shifted by 90 degrees, and I just have to figure out which way to shift it. Well, if omega t is 0, minus cosine is going to be minus 1, right? Because cosine of 0 is 1. And so sine of what angle gives me minus 1? Sine of minus pi over 2. And so that means I'm going to have omega t minus pi over 2 is exactly the same as minus cosine omega t. So that means V sub c is equal to I max over omega c times sine of omega t minus pi over 2. How does this look like Ohm's law? It's proportional to current. That looks like Ohm's law. And so we define, I almost wrote R, X sub c is equal to 1 over omega c is what we call the reactance of a capacitor. Now in class yesterday, between Carrie and me, we talked about the reactance very briefly. Reactance has its name, reactance, because it's how the capacitor, or as we'll see in a moment, an inductor, reacts to current and voltage. A resistor resists charge going through it. It takes away energy. An inductor or a capacitor doesn't resist, but it reacts to store energy and then give it back. So that's why we have a different word. They're based on actually what happens. And so this reactance, it has units of ohms again, but the thing that's curious about it compared to resistance is it depends on the frequency. So if omega is bigger, what's going to happen to the reactance of my capacitor? It gets smaller. So if I have a really high frequency, then I'm going to have a really low reactance. I'm not going to have much happening with my capacitor. It's going to behave essentially like a straight wire at very high frequencies. But at low frequencies, well, what is a capacitor? It's an open circuit, right? There's no connection. So at low frequencies, it becomes a bigger and bigger resistance so that at a frequency of 0, it's an open circuit. But then we have this part right here. It's still a sinusoid, but it's pi over 2 or 90 degrees out of phase with the current. So when the voltage is at its peak, the current's going to be 0. When the voltage is 0, the current will be at its peak. So with the capacitor, we have that out of phase. What's the relationship between the two? Well, we can just come and look at this equation here. I equals C dV dt. And just like I did yesterday, I can graph the voltage curve and then take the slope everywhere. And so if I do that, I would have, here's my voltage curve. And my current curve is just going to be taking the derivative. So the current's going like this. And now we have what is correct. And I know what I did wrong yesterday. It was with the inductor that I had it. And I know it's the sign convention is what I did wrong yesterday. And so we have the one that reaches its peak at the earliest time is the current. And so we use ICE to remember the phase difference that the current in a capacitor leads the voltage, the EMF. So the E in ICE stands for EMF. So the current leads the voltage means that the current is going to have its peak at an earlier time than the voltage. So the red line, the voltage had its peak out at this time. the current, the blue one, had its peak back here. And so that's what we mean by leading. The one that's leading here is the current because it came first. The one that's lagging is the voltage because it reached its peak later. So now we found the equation for the voltage across the capacitor, and we have the equation for the voltage across the resistor. Now we can find the voltage for the power supply. How do you find the voltage for the power supply? Let me remind you of what the circuit looks like. Yeah, we use Kirchhoff's voltage law. On a complete loop, I have to have the voltages add up to 0. So I would take my loop here and make a Kirchhoff's voltage law equation that says the voltage from the supply minus the voltage drop across the resistor minus the voltage drop across the capacitor is equal to 0. So therefore, the voltage across the supply is equal to the voltage across the resistor plus the voltage across the capacitor, where I have assigned plus minus, plus minus, plus minus for my directions. So then I have to add those together. Well, that leads us to our own special little problem, the problem that we'll be exploring in lab today. How do we add these when we have a sine of omega t and a sine of omega t minus pi over 2? And I know at least 4 people know the answer. But when we add these, we have to add them at any time, right? And at any time, it's going to have to be true. So what we do is we say, and I have to insert a page here. I'm sorry, I didn't think about doing that earlier. Page manipulation, insert. And if I've learned anything, it's that it's not going to work the first try. Because it says, well, actually, maybe they fixed that problem. Nope, they haven't. It puts it after the first page no matter what you do the first time. But after that, you should be able to move it to insert. Now, see, its position is 4th page. Now we have it right. So if we want to add these, what we do is we say, okay, I have voltage that is changing sinusoidally. And I can take a sinusoid and say, okay, if I have something that's going in a circle, there's a circle, I'm going to consider just, okay, that should have drawn a line. That's troubling. That's more troubling. When it fails, we kill it sesame. I want to get pizza, and my technology is failing me. It's like my wife must be working against me here, doesn't want me to have the unhealthy food. Okay, so I have that circle, and the horizontal part is going to represent the actual voltage. And so if I have an equation that says voltage across the resistor is equal to Ri max sine of omega t, that's the same as having a vector that goes from the center out to a point on that circle, the circle having a radius of Ri max. Well, okay. This is sine. Let's change from sines to cosines. All it does is change you by, 9 degrees, and then I don't have to redraw my picture. So I changed from sine to cosine. I'm going to change both for the resistor and for the capacitor. So I'm going to put voltage capacitor is equal to I max X capacitor times cosine of omega t minus pi over 2. Okay, so now I have this angle is omega t, and the horizontal part is going to be I max r times cosine of omega t. And the vertical part is, I don't care. Right? All I care about is the horizontal part. Now, what about the voltage across the capacitor? Now, for the capacitor, I'm going to have a different circle. So let me make a bigger circle or a different circle. Perfect. Okay. I wonder if it will work if I try it like this. Clearly not. How can I do this? Come on. All right. Freehand it is. Here is my circle. Shush. It's just as perfect as the other one. There's my circle for the capacitance. Now, the capacitance was minus pi over 2. So it's going to be wow. I am on top of things. I will never rush again. Come on. I have to erase each one of those individually. So I'm going to measure it from minus pi over 2 out the same angle, omega t. And so my capacitance is going to be this perfectly straight line like that, with its magnitude being I max xc, where remember xc was 1 over omega c. And then how do I get the total voltage from this? I'm just going to take the two parts that are in the horizontal direction. And so I take this part that is here plus, actually I made them so they're exactly the same. That was an accident. Plus this part that's here, and I add them together. And if I add them together, I could do that graphically by just using tip to tail addition. So I'm going to make my parallelogram tip to tail addition. And now we can see, okay, the total, when I add these two together, would be a line that goes from the starting point to there. And just the horizontal portion would be my voltage total. So we will define an angle here that mathematically we determine. I'm not going to worry about determining it right now, but that mathematically we can determine. And we can add these as vectors. I added them as vectors. They were 90 degrees out of phase because the sines were 90 degrees apart from each other, or the cosines as I changed it to, so I didn't have to change my picture. When we do this, we talk about these as phase vectors, and thus we have the term phasor. So the phasor is the phase vector. It has two important pieces. It has the magnitude and the angle. That angle is only this portion. We assume that they both have the same omega t. And so if I take my picture, as t changes, what's going to happen to my picture? The entire picture is going to rotate, right? So it's like you just take the picture and you spin it. So by convention, we just align our picture so that the Ri max is on the horizontal axis. Basically, we're taking time as 0 from my cosines. And that's how we draw our picture. So we draw the resistance voltage as a horizontal line. And we draw the capacitance voltage as a line that's going downward. And when we get to inductance, remember in class I'd said the Eli, the Iceman. In the inductance, you have the Eli, the voltage leads the current, and so that one's going to be vertical upward. And so we just take our voltages and we graph them as vectors with the resistive part horizontal, the inductive part vertical upward, the capacitive part vertical downward. And then we add those vectors together to get our resultant, and that tells us what the total voltage is going to be. And so for this case, it depends on what the values of omega and C and R are, what my answer is. But I get it by just taking those, redraw the picture. So I have, this is Ri max. This is X sub C I max. If I add these together, move it out there, and I have a pretty easy resultant here. The resultant is going to have, actually, different pen, different rules. The resultant, we use the angle phi to stand for phase. And based on this triangle, you can see what the resultant is right away. Notice I have I max on both sides. I have a right triangle. What's the trigonometric function that relates my angle to my adjacent opposite sides? So I have tangent of phi is equal to the opposite side, xc, times I max, over the adjacent side, r, times I max. Cancel those I maxes. And I'm going to have phi is equal to inverse tangent of xc over r. So I can calculate that phase angle for my voltage supply very simply. Now that we've gone through all of this phasor work. Going through the phasor work has the confusing part of understanding what it means. Once you get past the confusing part of understanding what it means, it's really easy to work with. And that's why we do it, because it's easy to work with. Because we can just take and plot on the horizontal axis. If you've taken, no one here has taken complex analysis, right? No. If you've taken complex analysis, I tend to say the real and the imaginary axes for these, because that's how you do complex analysis. You put horizontal as real and the vertical is imaginary. But you plot it out there, and it's easy to get your resultant. So that's what we're going to be doing in lab today. We're going to be making phasor diagrams, making these little vector diagrams to show how the voltages add in an RLC circuit, one that has inductors, resistors, and capacitors. All right, let's get back to the lecture. What about inductors? They're fuzzy, apparently. In the inductors, you see I have a lot more preparatory work here. For the inductor, we have Faraday's law of induction has a minus, and what does the minus sign mean in that equation starting? What does it tell us?
That's the EMF opposing the motion.
Yeah, it tells us that we have to look at Lenz's law because we're going to have our induced voltage creates a current opposing the change in flux. That's what you're saying, right? So it's really something to tell us about the direction. My problem in class yesterday was I left that in there like it's the gospel. And we define our directions so that you see that bottom equation, it doesn't have the minus sign. Your inductance is a positive value, and we threw out the minus sign. We just said, and the next slide is one that we had last class period, we said that we're going to use a sign convention like this. And using that sign convention then, the voltage drop is L di dt. And if somebody wants to start getting upset, you can say, well, I said a voltage drop. What do you think that minus sign means? Right? It means we're measuring the direction of the drop. I don't really care. What I do care is that we paid attention we know what the sign is here. The voltage difference is L di dt. So we went through all of this in class yesterday. There's no point in regurgitating it. Using this voltage as L di dt, let's look at a circuit that has a resistor, an inductor, and a power supply. And once again, the current is going to be I max sine of omega t. Well, instantly we know that just like the first time through, the voltage across the resistor is going to be I max R sine of omega t. What about the voltage across the inductor? Change colors. How do we find the voltage across the inductor? If I was smart, I would color code with green for inductor and red for the resistor, but we'll all right past that point. How do we find the voltage across the inductor?
L divided by C.
Yeah, we just do equals L di dt. Take the derivative of sine. Derivative of sine is cosine, but you got to bring out the omega. So that's going to be L times omega I max cosine of omega t. But just as before, we can use the definition. Cosine of omega t is the same as sine of omega t plus pi over 2. This time it's plus pi over 2 because we didn't have that minus sign. And so the voltage across the inductor is equal to L omega I max sine of omega t plus pi over 2. So we define, again, a reactance. What should our reactance be for the inductor? I put X instead of I here because I wasn't thinking clearly. Were you wondering where did that X come from? It should be L omega because L omega is the thing that current's multiplied by. So notice our reactance for an inductor, as omega approaches 0, what value does the reactance approach? 0. Well, an inductor is a wire that's wrapped in loops. In the DC case, it's just a wire. What should the resistance be for a wire? 0. So it makes sense. The reactance is 0 if it's DC because it's just a wire. But if it's not DC, then you're going to be building and collapsing magnetic fields, and you're going to have a reactance. And if the frequency goes super high, what's that going to become? It's going to become very high. So if you have a high frequency, it's going to be a big block to current. Low frequency, it passes right through. Capacitor was just the opposite. At low frequency, the capacitor is a block for current, but at high frequency, it passes right through. So they work oppositely. This allows us to make filters. So if you ever listen to music, which probably all of you do, back in the day, before you had electronics to do everything for you, you would make a filter that used inductors and capacitors. If you make something that looks like this, here's your sound, and here is an inductor, here's a capacitor, and heck, I'll put a resistor here. If you have a low frequency, then the current's going to be really low, because in low frequency, you're going to have the capacitor blocking current. If you have a high frequency, your current's going to be low because you have the inductor blocking current. Somewhere in between, then, there's going to be a frequency where you have a maximum. We call that resonance. So if you're making a radio tuner, you adjust it so it has a resonant frequency equal to the frequency that's coming from your radio station. And then it will just basically not respond to other frequencies, and that's the only one that you're picking up. Or if you want to make an equalizer, you make a bunch of these circuits and each one has a resonance at a different point, and you put your sound signal, so now not the radio wave signal, but the sound signal, through these, and the one that has, a frequency range from 100 to 200 hertz, you add that, and that's how you make an equalizer. You make different circuits that have different ranges of frequencies that they're going to allow through, and then you add up how much from each one. Question, Brady? I did. Thank you. It was rather appalling to me. I clearly didn't cover this enough, and making mistakes like this doesn't help. Because on the test, a lot of students didn't know how to draw a capacitor. I know I drew them and talked about its shape, but apparently I didn't emphasize it enough because, it was a problem. So let's analyze how a circuit like this works. This is what our entire lab is a circuit like this. So here's a circuit, looks just like mine, except for the R and L as switched positions. And now we have a current of I max omega C, or I max sine of omega C going through. So now with this circuit, we can use what we've already done to calculate what the voltage is across each one of the individual things. We have the voltage across the resistance is I max R sine of omega t, which we write as simply I max R angle of 0. Why angle of 0? Because it was omega t plus nothing. And then we had the capacitor was equal to I max X subcapacitor sine of omega t minus pi over 2, which we write as I max X sub C angle minus pi over 2. And finally, the voltage across the inductor, I max X sub L sine of omega t plus pi over 2 equals I max X sub L angle pi over 2. So that's how we write the phasors for each of those. The middle one is what it means. The one on the right is how we write it. And now that we have these, if we want to find the total voltage, we're going to have to add these up as vectors. So I make my little grid here, and here's going to be the resistive part. Up here will be inductive, and down here will be capacitive. Capacitive, I think that's spelled right. And so we have each one of these that we have to add. So we have this here for the voltage across the resistor. This here for the voltage across the capacitor. And this here for the voltage across the inductor. So if we add these together, what are we going to get? I always add them in a specific order. I do the inductor first, so I put this first. How do we add vectors? Just remind everyone with your blurting out. Tip to tail. So here I've shown 3 randomly drawn phase vectors. And if I add them tip to tail, then there's my V total. Is my V total equal in magnitude to any one of these? No. Is it equal in magnitude to the sum of each of the magnitudes? not to the sum of the magnitudes, because we have different directions. And so how can I find the magnitude of V total here? That's right. The magnitude of V total is equal to the square root of the horizontal part squared plus the vertical part. Notice it's VL minus VC because VL was up and VC was down, quantity squared. Now, since the magnitudes of each one of these were multiplied by current, I will take the V total divided by current is equal to this over current, and I'll call that the impedance, which we use Z for. And notice dividing by the current is just going to make the VR becomes R. The VL becomes XL. The VC becomes XC after you've divided the I out. So I have, and once again I ran out of space, but of course now it's going to work the first time through because we've done it once. Page manipulation, insert. Uh-oh, where'd it go? Okay, so it didn't work then. Now it's going to work. Except for now it's back to dark gray. I should have noticed if it goes to dark gray, it's not going to put it in the right place. Okay, so now we have Z, based on what we just did, is equal to the square root of R squared plus XL squared minus XC. XL minus XC quantity squared, my mistake. So we talk about this impedance as the combination of the resistance and the reactance. It's telling us how current is being impeded when it goes to the circuit, whether the circuit's going to give it back, reactance, or it's going to absorb the energy, resistance. The impedance is including both. So that's the impedance, Z, and of course the phase angle is going to be inverse tangent of the opposite side, which is the XL minus XC, over the adjacent side, R. And so that's the phase angle. Or you can do the phase angle one different way. If we look back at our picture here, wasn't it here where, or did I not draw the picture? I was sure I did. Okay, here we go. Here's the picture. The phase angle here has for its opposite side VL minus VC, right? This distance here is VL minus VC. For the adjacent side, it had VR, but we can also use cosine using the hypotenuse. And so if I do it in terms of cosine, it would be cosine is adjacent over hypotenuse. The adjacent was the voltage across the resistor. If I divide out the current max, because they all have the same current max, that would be the resistance over the total impedance Z. Total impedance being the total voltage divided by current again. And so this is actually, the second part is how we usually define it. That phase angle is the inverse cosine of resistance over the total impedance. That's actually really important. This is my final step. Oh, wow, I got 3 minutes. We actually just took the time. The final step is how much power is going to be used by a circuit like this? What's the equation for power? IV. But how much power does an inductor use? Average power is always 0. What about a capacitor? Average power is 0. So it's only going to be the resistive part of the power that's actually used. So in circuits, we often calculate the apparent power, which is the maximum current multiplied by the impedance, well, not the impedance, by the maximum voltage. But that's not the actual power. The actual power is going to be the maximum current just times the voltage across the resistor. And so we can get that using the phase angle by taking the power is equal to voltage times current times cosine of that phase angle. Because that phase angle was the angle between the maximum voltage and the total voltage and the resistive voltage. Yes, yeah, that should have been V max and I max, or yeah, V max, I max. Yeah.
What do you mean by Vmax? So do you mean the total voltage?
The total voltage coming out of your supply,
Okay.
and the total current coming out of your supply, the maximum for each, and then cosine of that phase angle. And so if that phase angle is 0 degrees, then your actual power will be equal to your apparent power. And you'll pay for what you're using. If that phase angle was 90 degrees, that is if it's purely inductive, let's say, or purely capacitive, you're not using any power. But you would still get charged for power from the power company. So you don't want to have that phase angle 90 degrees because you're charged for power you're not using. What do you want the phase angle to be? 0 degrees. So you're charged for the power you're using. That is, so you're using the power you're charged for. Because you're charged for voltage times current. And you want what you're using to be as close to that voltage times current as possible. So in something like a motor, you have a refrigerator. Refrigerator has an electric pump. Electric pumps are made with a bunch of windings of wire. But what's a winding of wire? It's an inductor. And so that pump is a big inductor. And so when the pump turns on, you have a big inductive load, which means that you're going to have a lot of apparent power that's not actual power. And so to make it so your refrigerator doesn't cost you as much to do the same amount of cooling, you would want to put something like a capacitor in parallel with it to bring the phase angle closer to 0 when it turns on. The capacitor in parallel doesn't use any energy, doesn't give back any energy, but it makes it so it doesn't look like you're using as much, even though you're using the same amount. Okay, we're out of time. Now you should understand much better for lab tomorrow, or today.